Testing, 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 one, two, three. Oh, here it comes. Oh, all right, it's working. Yep. Oh, here it comes. All right, it's working. Okay. Now I really want to make a video on multiple subjects. Let's see if it's done. No. There we go. The things I've been thinking about. It's hard when you're streaming the video to separate it. If you stop streaming and start again, it might add it on to the next video and even fuck it up. So I'm just gonna stick with the chemistry thing. Because one of the things I've been thinking about is water chemistry. Water chemistry. Because really, in terms of physics that is directly important, it's the fact that, alchemy, the study of chemical and substances in general, and their interactions with each other, were turned into physics by the theory of quantum mechanics. But when you see that it was applied to quantum mechanics for a specific purpose, to explain the atom, right? A lot of the weird things are deductions or inductions made from quantum theory, whereas really, in the most direct sense, um, it's about atoms, right? We have, and specifically water, because the things that, life is a property of water. But of course, water and carbon and, oxygen and hydrogen that make up the organic, like, Lego set, um, they also interact with, other things, the heavier elements that have more complex shapes. But those are more rare too. So that's the funny thing about organic chemistry, is that it's made of, the universe's most common elements. Um, so, yeah, I've been looking into water chemistry lately, um, and therefore chemistry in general. Uh, taking another iteration over my understanding of how this works. Because, chemistry is like Legos, but it's more complicated. There's more than just one kind of, plug type. Um, and yet, if you just look at the organic chemistry, the carbon, hydrogen, oxygen, water is an example in that sense, but carbon has to be involved for it to be called organic chemistry, but all organic chemistry is water dependent, let's say. So, I've been looking into, again, what is the nature of how these things plug together. There's a couple different ways. Because on the one side, there's these covalent bonds and the electron affinity, right? To make molecules with. But then there's also ionic bonding, like a sodium and a chloride. They don't share the electron. they rip electrons, they steal electrons and keep them to themselves, and then they become little, magnets, plus and minus, that want to pull together. But then there's also an in-between example with water, and other hydrogen bonding, where the oxygen has the two hydrogens on there, not across from each other, but like, Mickey Mouse ears. And that hydrogen ends up being able to, wanting to attract the oxygen. The atom itself becomes polar, it's unbalanced electrically. They share electrons because of this electron affinity, which is its own effect. And that ends up making the electron flow throughout the atom unbalanced, in the sense that one side becomes more negative and the electrons spend more time, and the other is more positive. And this is all, it's a complex calculation, but this is all, based on the fact that the electron is like this electron plasma. It wants to spread out into a bubble, but if it has more energy, it's like the string of a guitar, and with more energy, it gets some higher frequency vibrations in it, and it gets a more complex shape, at least until it drops down to its lower energy state. So that's why I was talking about neon. Now, neon is good to think about because it's one of the noble gases. And what's going on with the noble gases is that they're all full up. The electron affinity is satisfied for them. So they don't have a Lego plug, and they don't want to plug into anything else. Helium, neon. We're going to talk about neon because neon having 10 electrons is fully satisfied up to its p level of shells. So it doesn't want to connect with anything, right? Because, okay, here's the thing. So an electron can't be, it can't be in the same space as another electron, just like any physical object, just like it can't be in the space of the proton. But that's quantum mechanically based on the fact of it having the same quantum values, and the one quantum value that it can differ with another electron is its spin. Now the spin is the idea of spin comes from the fact that the electron has a little tiny magnetic field, like a planet or something. How can that be if it only has a negative charge? And the answer could be, at least metaphorically, that if you have a magnetic ball that was, negative, and you spin it, it'll create the polar magnetic, um, the dipole, since there can't be a monopole. And everything seems to have the spin, but the spin can be zero, right? So with electrons, the spin's negative 1/2 or positive 1/2, and you could call that negative 1 or positive 1. They just, when they did all the calculations, it turns out to be, it's like, oh, it's a half of what we originally thought the unit would be. And if two electrons have the opposite spin, then they tend to want to pair and create one of these orbitals that would be completed. And so the neon, this blue one, is two electrons that are paired together in a Cooper pair. That's an S. And then there's another spherical one, another S orbital, I believe. Doesn't it say that yet? The 2ns. Another pair of electrons. And then by the next step up, as you get more electrons or more energy, you have the p ones. And this is a pair, this is a pair, and this is a pair of electrons, right? And so they'd fill out that way. Now, you know, the mathematics of quantum mechanics explains why they pair up. As far as I'm concerned, it's just like that's one of the rules. Like, positive and negative sides of a magnet attract. Oh, another rule is, at this level at least, electrons want to pair up. And if they've all paired up, they'll have this nice symmetrical shape if they have 10 electrons. Now, if there's more electrons, you're going to start to get the like down here is the first ones, what a hydrogen would have. Then you've got these three, which add up into that, this shape. And then in the D, you start to get really weird ones. And then up here at F, so at the things further up, these other gases, xenon with 54, it's going to start to have the all of the above with all of these things adding up together. So it's a weird little bubble. Now they don't really. It's hard to calculate what these other shapes are with these double donuts and stuff because it's like you have a magnetic plasma, the electrons in these pairs. The plasma is repelling itself, right? So naturally, it makes sense for a magnetic soap bubble, even in a vacuum, to be a little bubble because the negative charge of the electron, soap bubble or whatever, is, it's all repelling itself. It's going to repel itself just enough until the pressure is balanced or whatever. You get these more complex bubbles because basically it's like if you agitate the water in an ocean or a pool, it's going to get more and more bumps in it. If you hit a guitar string harder, uh, then instead of just having the one, wavelength, it'll start to have all of these complex wavelengths shooting back and forth, reflecting in the string. And that's what these ones are here higher up. And it's important to remember that in the noble gases like neon, these are all full. But in something like oxygen, this is a different rendition. It doesn't show them as these figure eight things. They are the figure eight things. This is also a fair representation, though a little not quite as good, especially since look how big the nucleus is supposed to be. But the fact is, a lot of these cones, the electrons are not likely to be there. Those are fainter. So it is darker here and then very, very faint because it goes down through the nucleus and none of the electrons can be in the nucleus. So there's almost an exclusion zone and it does kind of match up with the S sphere of where it has to be out here, but this should actually be a little more shaped like that. But the difference between this and this, besides the way they're rendered, is that in the oxygen has 8. This has 10. Now 10 what? 10 electrons or 10 neutrons, because that's the point. If this isn't ionized, it's going to have an equal number of protons, not neutrons, sorry, protons and electrons. This only has 8. But because of the electron affinity thing, it still wants 10 in a sense. There's some energy that it would save if it could pair up its electrons, right? Now, an example of that would be, in the simplest example, hydrogen. Okay, so here's hydrogen. Ignore these for a second. Hydrogen just fills this spherical first shell. and it only has one electron normally. So it's balanced with one proton, one electron, but that shell would like to pair up with another electron. The problem is it can do that, and that's somewhere in here. Oh, here. A hydrogen anion. An H minus atom is a hydrogen that has actually gotten that second electron, so that there's two in its shell, making it have a negative charge. Now, the reason and it says in the Wikipedia that in the star and high energy places that happens. I would imagine it also happens in low energy places. But the issue is that you've got to be fed that electron. It's so easy to lose the electron. Um, there's a certain amount of energy. If you look in this, like, here's the amount of energy it gets from taking the electron. Here's the amount from losing, the electron in the ground state. And the fact is, the way they calculate these things is things want to get their lowest state and shoot off a photon. That's what will happen over time. Things will get to their lowest state, shoot off a photon. The lowest state of the hydrogen is this circle. But if a photon hits an electron that's in this bubble shape, it'll bloop out to this. And if it takes a couple more photons, it can stay in sort of this configuration and just zigzag it back in the 3 dimensions. But if it gets another photon, then it starts being this more complicated 4 bubble shape, or the donut shape, right? However, the issue here is if it gets this much energy, likely the electron's going to actually shoot off of the proton altogether. And that's where organic chemistry comes in, because things of this shape can take, a lot more energy and feedback it's more granular. Um, Here is an example of a carbon. Now, a carbon has 6, if I recall correctly. And so it also wants to be this shape, right? And when I say this shape, remember, these little tabs are where it can plug into another atom and make a molecule. Neon won't, because these plugs are full. You want to have one of the plugs that's empty. In oxygen, these 2 green ones are shown as full, but the yellow and the pink, they only have 1 electron. Therefore, they can bump into something else, like hydrogen with 1 electron. They'll start sharing electrons with the electron affinity, and then you get the issue of, by sharing an electron, a hydrogen is giving half an electron to the oxygen, and therefore, it's going to be positive or negative. It's a little more complicated than that, because it flows back and forth. But if you calculate where the current is over the course of the flux of the flow, and this yellow and pink can both bond, you can get, this is an oxygen we're looking at, you can get 2 H's on there, hydrogen, and have H2O. And the 2 hydrogens are, off at this 90-degree angle, but because they also repel each other, they bend out to a little bit greater, and that's why they're not straight across, but are at this angle. Now, in the case of carbon, what you have is, since there's only 6, like 8 is enough to put at least 1 electron in each of those natural noble shells. This is what it has when it's all full up. So since it's sort of a mutant, it's only got 6, it can't put one in every shell. So they sort of morph and tweak. They bend each other because the sharing has to get extra thick because it can't put one whole electron in each of the p shells, and therefore what happens is you get this distorted shape, which is like this. It's what you call hybrid orbitals, an sp orbital, and so it gets to be this hybrid. They're not, see, over here they're showing how there's a little bubble, but inside this bubble there's a little bubble in here that doesn't really matter because it's hidden, it's isolated. These four things are what it's going to bump into, and when you have things like graphene or pure carbon diamond, this tetrahedral shape is what defines the shape of those other carbon substances, from diamond to graphite to graphene. And it's why it's so flexible, because if all the molecules are Legos, the problem is with most of them, they're like specialty Legos that barely plug into anything. Whereas carbon, oxygen, hydrogen plug into themselves great. They plug into everything else at least a little bit. So they're this like lingua franca. Um, and then in the case of water, now this is kind of a low res thing here. So, but if you look, you could see there's an hydrogen, there's a hydrogen, there's an oxygen, right? Because when you have a connection like a square, these are water clusters. So the red is the oxygen and a water, and if you look really close, you can see there's a hydrogen and a hydrogen. At this size, you can't really see the hydrogen, but you need to remember, because one of the hydrogens is going to be moved out of the way. If four water molecules are making this little square, then there's four little hydrogens that have to be slided out, because what's going on here is that the oxygen in one water molecule is attracted to the hydrogen. This is a hydrogen bond. It's much stronger than the bond between the sodium and the chloride, a normal ionic kind of a bond. It has a sort of a special class, this hydrogen bonding, and uh, but since it's from the oxygen end to the hydrogen end, well, there's two hydrogen ends. It's in a little triangle, so it's going to be connected to one, and there has to be room for that extra hydrogen. Zoomed out, this diagram doesn't show the hydrogen too well, but it is important, because as you get these big structures like down here, both hydrogens have to be in the way, and you get situations where maybe the hydrogen wants to switch back and forth. It could be either hydrogen. There's room for it to be this way or that way. So you get a lot of complex shapes. These are water clusters. You get a ton of regular and semi-regular complex shapes in water molecule clusters. And what happens is, when molecules of any sort, but especially like organic, or the lighter molecules, common ones, they are going through water, and in the water, by random chance, there's all these different kinds of shapes. And as this molecule, say a salt molecule, runs into one of these and bumps through it, because of the regularity, the magnets are all holding on. They're not holding on so strong that they can't be broken apart, but as the salt cluster comes through it and breaks it apart, it fights back a little bit, and it sort of scrubs that other molecule. And in many cases, at the organic chemistry level, the weights, the atomic weights, um, of 30 or less, or rather, the proton counts of, well, 10, but around 10 and less, they're very susceptible to being scrubbed this way by these little water magnets and broken apart. And of course, my premise, um, uh, that life is a property of water is leading to this conclusion, or vice versa, that uh, this process, this chemical process that water can do because of these hydrogen bonds, because of this sort of advantageous, unique, certainly, shape of the water molecule, it is doing a data reduction process. It's breaking up the sodium and the chloride and saying, oh, look, sodium chloride. It's taking up complex organic molecules and sugars and stuff and dissolving them down and going, oh, it's this and that and that. And so even though it has no, obviously it doesn't process the information, right? It doesn't build it back up. It just breaks it down. Breakdown. It's like a data reduction process. It's everything but the part where you go, ooh, look what I've learned. I can do something with that. Now I'll build something back up. No, water doesn't do that. It's not thinking, but it is doing the mechanical work of breaking up chemicals into their constituent components. And in a sense, in a way that's like, I mean, I think here's for example, by taking seawater and you analyze in seawater, there's all sorts of things are dissolved. Carbon, tons of carbon, right? Um, Literally millions of tons or whatever. Like you could get as much gold out of seawater, dissolved in seawater, as in the crust or whatever. I mean, there's tons of it in there, of everything. It's all dissolved, not literally everything, but almost everything. Water is like very general purpose, universal solvent. So if you took the seawater and then you boil it, and all the things you have to do, find out what minerals are in it, and find out, oh, there's this much gold and there's twice as much uh, lead, or I don't know what the numbers are, a billion times more iron, whatever. Those numbers are what is in the Earth's crust, because the water has been dissolving the Earth's crust, and that's what I'm saying. So it's like a measurement device. You put water in somewhere for a million years or billions of years, whatever, and then you take the water out and you test it. It'll tell you what the composition is of the whole thing, that the water was sitting in. That is data reduction, right? And what I'm telling you is the process of data reduction, in the sense that it has to do with how these things plug together, right? Two oxygens can plug together because, unlike this neon, some of these shells, two of them, are missing an electron. And besides the whole thing where plus attracts minus, um, electrons, when these shells of two atoms bump together, shells where they only have one electron, they want to share, and you get a figure eight or a figure double eight thing going on. Whereas with the neon, they're full. So if a neon bumps into another neon or even another oxygen, it goes, no, thank you, I'm full. But two oxygens are like, ooh, I'm missing a piece too, and you're missing a piece. Let's plug together like two pieces. That's how the Lego system works. Cheers, everybody.